Learning goals. Welcome to this learning session on mole concept, calculations, and standard solutions. In this course, we shall address fundamental chemical principles and laws, chemical nomenclature and oxidation states, chemical formulae and mass composition, chemical reactions and mole ratios, stoichiometric calculations, and reaction yields. There will be a quiz at the end to test your knowledge.
Introduction to Chemical Principles. This section introduces essential skills in physical chemistry, focusing on matter and its properties. You will learn IUPAC nomenclature for inorganic compounds, how to write compound formulas based on chemical laws, and the process of balancing chemical equations. A key objective is to deepen your understanding of chemical reactions through stoichiometric calculations. These calculations are fundamental to predicting the quantities of reactants and products in chemical processes, which is crucial in both academic and industrial settings. Key ideas in chemistry. Understanding fundamental terms is crucial for mastering chemistry. Key ideas include the oxidation number, which represents the charge of an ion in a compound, and different types of chemical formula. Empirical formula is the simplest ratio of atoms of each element in a molecule. Molecular formula is the actual number of atoms of each element in a molecule. Structural formula shows the arrangement of atoms in a molecule. Additionally, prefixes like mono, di, tri, and tetra indicate the number of atoms of an element, while suffixes such as ed, ate, and ite denote the type of compound or ion. Reactants are substances at the start of a reaction, and products are the substances formed. Stoichiometry and yield concepts. Stoichiometry is the quantitative relationship between reactants and products in a chemical reaction. It allows chemists to predict the exact amounts of substances involved, which is critical for efficient chemical synthesis and industrial processes. Key terms in stoichiometry include coefficient, the number placed in front of a chemical formula to balance an equation; mole ratio, the ratio of moles between two or more substances in a balanced equation; yield, the amount of product obtained from a chemical reaction. Further concepts define the efficiency of a reaction: actual yield, the amount of product obtained in practice; theoretical yield, the maximum amount of product that could be produced based on calculations; percent yield, the ratio of actual yield to theoretical yield expressed as a percentage; limiting reagents, reactants completely consumed, limiting product formation; excess reagents, reactants left over after the reaction stops. Rules for assigning oxidation numbers. The nomenclature of inorganic compounds relies heavily on the oxidation number system. The oxidation number of an atom indicates the number of electrons gained or lost when forming a compound, providing insight into its chemical behavior. Key rules for assigning oxidation numbers include: the oxidation number of elements in their elemental state is 0. Oxygen typically has an oxidation state of -2, except in peroxides 1 and superoxides 1.5. Hydrogen is +1 when bonded to a nonmetal and -1 when bonded to a metal. Furthermore, the oxidation state of an ion equals its charge. For a neutral molecule or polyatomic ion, the sum of all oxidation numbers must equal the total charge on the entity. For example, in H2O, oxygen is -2 and each hydrogen is +1, summing to 0 for the neutral molecule. First, name the cation, positive ion, which is typically the metal. Follow the cation with the anion, negative ion. The anion is named by replacing its suffix with -id. For example, chlorine becomes chloride and oxygen becomes oxide. For metals with atomic numbers above 20, or those that can form multiple stable ions, their oxidation state must be indicated using Roman numerals in parentheses after the metal's name. This is crucial for distinguishing compounds like iron 2 chloride, FeCl2, from iron 3 chloride, FeCl3. This systematic approach ensures clarity and consistency in chemical communication worldwide. Naming simple acids and oxoacids. Simple acids, also known as binary acids, are composed of hydrogen and one other non-metal element. Their naming follows a specific pattern. Use the prefix hydro, followed by the root name of the central non-metal atom, then the suffix -ic, and finally the word acid. For instance, HCl is named hydrochloric acid. Oxoacids are more complex, containing hydrogen, oxygen, and another element, usually a non-metal. Their naming convention involves prefixes like oxo, oxo, trioxo, or tetraoxo to indicate the number of oxygen atoms. This is followed by the root name of the central atom. To complete the oxoacid name, add the suffix -ate and indicate the oxidation state of the central atom in Roman numerals and brackets, then append the word acid. For example, H2SO4 is tetraoxosulfate, V acid. This systematic approach helps differentiate between various oxoacids with the same central atom but different oxygen counts or oxidation states. Naming complex inorganic compounds. Naming acid salts requires a specific sequence. First, the metal cation, then hydrogen, and finally the oxoanion without the ion suffix. If the cation's atomic number is above 20, its oxidation state is indicated with Roman numerals. For example, NHSO4 is sodium hydrogen tetraoxosulfate. Simple non-ionic compounds are named by stating the electropositive element first, followed by the root name of the anion, and ending with the suffix -id. For instance, HCl is hydrogen chloride, and SiC is silicon carbide. This applies to compounds formed between two nonmetals. For molecular compounds where two elements form multiple compounds with different oxygen counts, name the electropositive element first, indicate its oxidation state in Roman numerals, and then name the electronegative element as usual. Examples include CO2 as carbon, IV oxide, and N2O3 as nitrogen 3 oxide, highlighting the varying oxidation states and oxygen numbers. Naming hydrated salts. Hydrated salts are ionic compounds that contain water molecules within their crystal structure. Naming these compounds involves a specific three-step process to accurately reflect their composition. First, name the anhydrous, water-free part of the salt, as you would any other ionic compound. Then, use Greek prefixes such as mono, di, tri, tetra, penta, hexa, hepta, or octa to indicate the number of moles of water of crystallization present in the formula. For example, penta for 5 water molecules. Finally, add the suffix hydrate to complete the name. For instance, CuSO4 5H2O is named copper 2-tetraoxosulfate V pentahydrate. This detailed naming convention is essential for distinguishing hydrated salts from their anhydrous forms, as the presence of water can significantly alter their physical and chemical properties. Types of chemical formula. A chemical formula is a concise expression that represents the chemical composition of a compound using atomic symbols. It provides fundamental information about the elements present and their relative proportions. There are 3 primary types of chemical formula, each offering a different level of detail about a compound's structure and composition. These include the empirical formula, molecular formula, and structural formula. The empirical formula shows the simplest whole number ratio of atoms in a compound, while the molecular formula indicates the actual number of atoms of each element in a molecule. The structural formula goes further by illustrating how atoms are bonded to each other within the molecule, providing a visual representation of its arrangement. Determining empirical formula. The empirical formula represents the simplest whole number ratio of atoms in a compound. Determining it is a crucial step in understanding the composition of unknown substances, often derived from experimental data. The process involves several key steps. State the mass or percentage mass of each element. Divide each mass by its relative atomic mass to find the number of moles. Determine the simplest whole number ratio by dividing all mole values by the smallest mole value. If necessary, scale up the ratios by a factor to obtain whole numbers. Finally, use the simplest integer ratio as right-hand subscripts to write the empirical formula. This method is fundamental in analytical chemistry, allowing scientists to deduce the basic building blocks of compounds from their elemental composition. Determining molecular formula. The molecular formula provides the actual number of atoms of each element in a molecule, offering a complete picture of its composition. While some compounds have identical empirical and molecular formulas, many differ, requiring an additional calculation step. To derive the molecular formula from the empirical formula, you need the compound's molecular mass. The relationship is expressed as molecular mass equals empirical mass n, where n is an integer representing the multiplier. Once n is determined, multiply the subscripts of each element in the empirical formula by n to obtain the molecular formula. For example, if the empirical formula is CH2O and the molecular mass is 180 grams per mole, n would be 6, leading to a molecular formula of C6H12O6, which is glucose. Percentage composition by mass. The percentage composition by mass of an element in a compound indicates the proportion of that element's mass relative to the total mass of the compound. This calculation is vital for understanding the elemental makeup of substances and verifying purity. To calculate this, first determine the molecular mass of the compound. Then, calculate the total mass contributed by the specified element, considering the number of atoms of that element in the formula. For example, in NH3, nitrogen contributes 14 grams per mole, and hydrogen contributes 3 grams per mole, 3 atoms x 1 grams per mole. The percentage is then found by dividing the total mass of the element by the molecular mass of the compound and multiplying by 100. For NH3, the molar mass is 17 grams per mole. Nitrogen's percentage is 14,182.35%, and hydrogen's is 370s through 100 equals 17.65%. These calculations are fundamental in quantitative analysis. Laws of chemical combination. The laws of chemical combination are foundational principles governing how elements combine to form compounds and how matter behaves during chemical reactions. These laws were crucial in the development of modern chemistry. The law of conservation of mass states that mass is neither created nor destroyed in a chemical reaction. The total mass of reactants equals the total mass of products. This principle is why chemical equations must be balanced. The law of definite proportion asserts that a pure chemical compound always contains its component elements in a fixed ratio by mass, regardless of its source or method of preparation. For example, water, H2O, always consists of hydrogen and oxygen in a 1:8 mass ratio. The law of multiple proportion, proposed by John Dalton, states that when two elements combine to form more than one compound, the different masses of one element that combine with a fixed mass of the other element are in a ratio of small whole numbers. For instance, carbon and oxygen can form CO and CO2, where the oxygen mass ratio for a fixed carbon mass is 1:2. Types of chemical reactions. Chemical reactions are fundamental processes that transform substances into new ones. They can be categorized into several types, each with distinct characteristics and applications. Understanding these types helps predict reaction outcomes. Combustion is a reaction with oxygen, producing oxides and often heat, like methane burning to form CO2 and H2O. This process is vital for energy generation in homes and engines. Synthesis reactions involve two or more simple substances combining to form a more complex compound, such as sodium reacting with chlorine to form sodium chloride. These are widely used in manufacturing salts, medicines, and polymers. Displacement reactions occur when one atom or ion replaces another in a compound, like magnesium displacing copper from copper sulfate. These are crucial in metallurgy and electrochemistry for extracting metals. Decomposition reactions are the opposite, where a compound breaks down into simpler substances, often requiring heat or light, such as calcium carbonate decomposing into calcium oxide and carbon dioxide. These are important in natural cycles and industrial processes. Ionic equations and spectator ions. An ionic equation is a chemical equation where dissolved ionic compounds are represented as their free ions. This provides a more accurate representation of what is actually happening in solution, especially for reactions involving precipitation or acid-base neutralization. Ions that exist in a chemical equation but do not participate in the overall reaction are called spectator ions. They remain unchanged on both the reactant and product sides of the equation. Identifying and cancelling spectator ions leads to the net ionic equation, which focuses only on the species directly involved in the chemical change. For example, in the reaction between potassium iodide and lead-2 nitrate, potassium ions K+ and nitrate ions NO3- are spectator ions. The net ionic equation shows only the formation of lead-2 iodide precipitate from lead-2 ions and iodide ions. This simplification helps chemists understand the core chemical transformation. Mole ratios in stoichiometry. The mole ratio is a fundamental concept in stoichiometry, representing the relative quantities of any two substances involved in a chemical reaction. It is derived directly from the stoichiometric coefficients in a balanced chemical equation. These coefficients indicate the number of moles of each reactant or product that would be consumed or produced under ideal conditions. For instance, in the reaction 2C plus O2, 2CO, the mole ratio of carbon to oxygen is 2.1, meaning 2 moles of carbon react with 1 mole of oxygen. Understanding mole ratios allows chemists to convert between amounts of different substances in a reaction. If you know the moles of one substance, you can use the mole ratio to calculate the moles of any other reactant or product, making it a powerful tool for quantitative analysis. Stoichiometric calculations. Entities and mass stoichiometric calculations enable us to determine the number of entities, atoms, molecules, ions, or the mass of substances involved in a chemical reaction. This is crucial for laboratory experiments and industrial production. To calculate the number of entities, write the mole ratio using stoichiometric coefficients. Calculate the number of moles of the known substance. Use the calculated moles and Avogadro's constant, L equals 6.02, 10^23 entities per mole, to find the number of entities, N equals NL. To calculate the mass of a substance, write the correct balanced equation. Convert the quantity of the known substance into moles, N equals m spore m. Use the mole ratio to find the moles of the substance being sought. Finally, calculate the mass of the substance using m equals n times m. Stoichiometric calculations are crucial for determining concentrations and volumes in chemical reactions. This module provides a guide to performing these calculations effectively. Stoichiometric calculations can also be extended to determine the concentration or volume of substances, particularly in solutions or gases. This is essential for preparing solutions of specific molarity or predicting gas volumes in reactions. To calculate the concentration of an analyte, write the balanced equation. Convert volumes to dmHu and use N equals Cv to find moles of known substance. Use the mole ratio to find moles of the analyte. Calculate the concentration of the unknown substance using C equals N over V. For calculating the volume of a substance, especially gases at standard temperature and pressure, STP, write the balanced equation. Convert the known substance's quantity to moles. Use the mole ratio to find moles of the substance whose volume is sought. Calculate the volume using V equals nVm, where Vm is the molar volume of gas, 22.4 mol at STP. Limiting and excess reagents. In many chemical reactions, reactants are not present in perfectly stoichiometric amounts. The limiting reagent is the reactant that is completely consumed first, thereby stopping the reaction and determining the maximum amount of product that can be formed. Conversely, the excess reagent is the reactant that is left over once the limiting reagent has been fully used up. Identifying the limiting reagent is crucial for optimizing reaction yields and minimizing waste in chemical synthesis. The procedure for determining limiting and excess reagents involves calculating the initial moles of each reactant, comparing these moles to their stoichiometric ratio, and then identifying which reactant will run out first. This allows for precise prediction of product quantities. Understanding reaction yields. In practical chemistry, the actual amount of product obtained from a reaction often differs from the theoretically calculated maximum. This discrepancy arises due to several factors that influence the efficiency of a chemical process. Reasons for not achieving 100% theoretical yield include: the reaction may be reversible, meaning products can convert back to reactants. Some reactants may undergo side reactions, forming undesired byproducts. It can be challenging to completely separate and recover all products from the reaction mixture. Understanding these factors is crucial for process optimization in industrial chemistry. For example, in pharmaceutical manufacturing, even a small increase in yield can translate to significant cost savings and increased availability of medication, highlighting the economic importance of maximizing reaction efficiency. Calculating percentage yield. The percentage yield quantifies the efficiency of a chemical reaction by comparing the actual amount of product obtained to the theoretical maximum. It is a critical metric for chemists to evaluate experimental success and industrial process effectiveness. The formula for percentage yield is percentage yield equals actual yield, the theoretical yield, to its 100%. The actual yield is the mass of product collected from an experiment, while the theoretical yield is calculated from the stoichiometry of the balanced chemical equation. For example, if a reaction theoretically produces 25 grams of copper sulfate, but only 20 grams are actually obtained, the percentage yield is 20 grams and 25 grams, its 100% equals 80%. This calculation provides a clear, standardized way to report reaction efficiency, allowing for comparison across different experiments or production batches.
Summary. Well done. You have completed the course Mole Concept, Calculations, and Standard Solutions. You should now be familiar with fundamental chemical principles and laws, chemical nomenclature and oxidation states, chemical formulae and mass composition, chemical reactions and mole ratios, stoichiometric calculations, and reaction yields. Should you need to revisit any of the topics in this course, please use the menu at the bottom of the screen.